Hey everyone, today I'm going to be showing you how solids of constant width could have led to the 1986 Challenger disaster. On January 28, 1986, around 72 seconds after liftoff, the Space Shuttle Challenger exploded, killing all 7 people on board. After a lot of investigation, it was found that there were 3 main reasons why the Challenger exploded. The first reason is due to bad joint design of the solid rocket booster. The second reason is due to bad O-rings that didn't perform well at the low temperatures in which they took off that day. But the third reason is something that you might not have heard of. The third reason could have been that the rocket boosters were not actually round like they should have been. So let me show you how this could happen. I have here a tube that's going to represent our solid rocket booster. So the problem with how they were measuring these solid rocket boosters is they would measure the diameter in 3 different locations along the tube. And if the diameters match, then they assumed that they were of equal roundness. For example, if I measure it here, it should be the same width as right here, which should be the same width as right here. And it looks like it all checks out. They're the exact same widths. But actually, even though I measured the same width across this tube here, it's not actually round all the way through. This is what it actually looks like inside of this. The problem with this method, as you can see here, is that you can have something that has a constant width all the way around it, but it's not in the shape of a sphere or a circle. So first we'll measure our sphere, and you can see that, of course, no matter how I roll it in here, it stays at the same width. But now let's test this out. It doesn't look like this would be the same width all the way around, but let's measure it. So I can measure it like this, but actually if I turn it any direction, it's the exact same width. No matter how I roll this in here, it stays the same width. The same's even true for this shape here. It keeps the exact same width no matter how I turn it. So these shapes here are called solids of constant width. So you can see how this can roll just fine, keeping the exact same width between the top of the glass and the bottom of the table here. It does exactly what a sphere would do under here. Let me show you how easy it is to make a solid of constant width like this. So I'm going to start off by drawing 3 lines. You can draw any 3 lines that intersect. So here's my triangle that I'm going to use to draw my curve of constant width. So start off at any of one of the 3 points of the triangle. I'm going to put the point of the compass at the point of the triangle here, and I'm just going to draw the curve between these 2 lines. Then what I do is I follow the path, the straight path along the compass here to the next point. Then I'm going to draw this curve. And then I go to the next point, and then draw this curve. And then move to the next point and draw this curve. Then move to the next point. Then move to the next point to finish it off. So this shape that we've drawn here now has a constant width. You can see that if I measure the distance between these 2 points, they're all going to be equal. And I can take any cross section of it and measure the distance as well, and they're all going to be equal. These shapes are often called false circles. They appear circular because if you take your calipers and try to measure the diameter of them, you always get this constant diameter, when in reality they're not circular or spherical at all. So it's believed that these solid rocket boosters might not actually have had a circular cross-section like they should have had. The test in which they measured the diameter wouldn't have caught if there were non-circular diameters. And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to subscribe if you haven't yet, or hit the bell so you can be notified when I release my latest videos. And thanks for watching, and we'll see you next time.